One day people will travel to Mars, hopefully soon, and perhaps come to live there, which means they'll need to grow their own food, and that isn't easy on a planet that's more barren than any desert or tundra. Probably one of the best science fiction films I've seen the last decade is The Martian, starring Matt Damon and based on the excellent novel by Andy Weir. And while it generally got great reviews, it was often criticized for a lack of realism about the astronauts' emergency potato farming on Mars. As far back as we could see Mars, even when we thought it had canals, we have discussed agriculture on the Red Planet, both in terms of terraforming the world and in terms of building domes and greenhouses. I thought today we would walk through the challenges and how we can address them so that future visitors or colonists to Mars don't have to import all their food and drink. And speaking of food and drink, we will be here for a bit, so you might want to grab a drink and a snack, possibly some potato chips, and don't forget to hit the like and subscribe buttons while you're at it. Now there's three obvious problems right out the door for agriculture on Mars, and that's the general lack of air, water, and sunlight. Mars does have all three, but its sunlight is weaker than we get, it has precious little water, and its atmosphere barely counts as one. It's a cold world whose highest recorded temperature is 70 Fahrenheit or 21 Celsius, while its average temperature is -80 Fahrenheit or -60 Celsius. Giving it more sunlight, air, and water would help fix that. But in its absence, you either need insulated domes or entirely enclosed options, like an underground hydroponics bay that's artificially lit. Our next problem comes down to the soil, or rather, the lack of it. Mars technically doesn't have any because by definition, soil must contain organic matter. And we currently assume life on Mars is either non-existent or ultra-minimal. Terran soil contains 50% air and water, 45% minerals, and 5% organic matter. Martian soil, on the other hand, is 98% minerals and only 2% air and water with zero organic matter. Not much can really grow in that. Although high in nutrients, Mars is basically just volcanic rock. It has various clay or silt-sized particles, but it's mostly sand. And as we'd expect from the red planet, it is iron-rich. Surprisingly, it's also rather homogeneous. Unlike terrestrial soils, which vary considerably by location, the dirt on Mars is similar all over. The planetary dust storms distribute the material. Mars does have all the nutrients plants need, and again is high in some. However, some of these minerals all spread pretty thin. The nutrients in the dirt are so low in many that we would need extensive fertilizer. In 2015 in the Netherlands, they simulated Martian soil and grew 10 crops in it, as well as trying it for simulated lunar soil. Those were chives, cress, garden rocket, leeks, peas, quinoa, radishes, rye, spinach, and tomatoes. Obviously, water and air were added, and while none of them produced as much biomass as on Earth, only spinach was particularly poor. They didn't eat any of it though because it was rich in heavy metals like arsenic and mercury, and everything was high in iron. We'll get to discussing those, as well as perchlorates in the soil, in a bit. Inspired largely by that movie, there have been experiments growing potatoes in Martian soil simulants as well as other Martian conditions, and with modest success, but everything does better once organic matter is added in. That will always be available after the first generation of plants and by the simple presence of humans, since we produce a lot of organic matter, but it nonetheless tells us that we need to be creating our soil on Mars, not just expecting to dump seeds in Martian dirt and having a garden grow. Speaking of gardens, we might imagine that plants we grow on Mars will primarily be for food or feed for animals, as well as for herbs for adding some flavor and smell. However, there's another important thing we might want to grow too: medicine. We are far from a short trip to the emergency room to get some antibiotics or painkillers, and any medicine sent from Earth has an expiration date. By the time we get any medication shipped to someone sick on Mars, they might already be dead. So we might want to be growing plants that have some kind of medical benefit too. There have been some early experiments to genetically modify fast-growing plants like lettuce to let us grow acetaminophen, the active ingredient in Tylenol. You could imagine using the same method to create a bunch of useful compounds that we are used to having on hand for first aid or common ailments, but we might also need some other pharmaceuticals that we don't need on Earth. For instance, since we know that humans lose bone density in space, we might want to start taking supplements that will help stimulate bone growth. So we probably have a mix of plants for food, feed, and pharma that we need to grow, and as I said earlier, insulated domes and underground artificially lit hydroponics are good options. Now if you're building a dome over something that's not much harder to give it a floor, and given that initial farms on Mars need to be pressurized and airtight, you need a floor anyway and are probably doing either hydroponics or raised beds to start. Algae grown in vats is a good way to get some initial biomass and potentially feedstock for plastics, including polycarbonate domes. It's also a good way to process Martian dirt into soil while you're building domes, so the first agriculture there might be setting up large insulated water tanks with grow lights in them. Those might be supplemental or primary depending on if using sunlight is convenient. How we cultivate crops depends on what the base's power situation and workforce look like, so let's discuss that first. The truth is, even on a 2-year round trip to Mars, it is likely to be easier to pack the food along than grow most of it, as dehydrated foods are pretty low mass, and you need equipment for growing food on the trip anyway, both in the ship and down on Mars. So we're mostly interested in plant growth on early Martian missions for supplemental fresh food, emergency medicines, and for scientific research into future space and Martian farming. We need something low on manpower, both to build and maintain. Robots might help, but they take mass too, and we need to know our power supply. For my part, I don't think any mission to Mars should fail to have a nuclear power source involved unless our solar power and battery options get way better than they are today. Admittedly, given how much they've improved in recent years, that is plausible. Alternatively, we have some very robust, lightweight, and safe atomic options, and unlike common light water nuclear reactors on Earth, anything going to Mars can't require lots of water to work. I suppose my ideal first attempt would be to send a nuclear power plant down to Mars first, near a preferred manned mission site, complete with some drone harvesters and a stockpile of LEDs, and automated manufacturing and refining gear so it could just land and start making and assembling big old algae vats for mass-producing biomass and fuel. That tends to be a bit beyond the scope of robot manned missions aiming to arrive before the first explorers, but I tend to feel that's about where our technology will be by the time the public permits a manned Mars mission. You might be wondering about that choice of phrasing, but right now Mars missions enjoy the general goodwill of the public, who don't really mind paying for one, though that's mainly because it's not seen as something that's about to happen. When a serious mission is on the table, it will start getting picked apart for many reasons, such as the mission's cost, odds of success, and what it will actually accomplish in the short term. For any plan to be approved, it is also going to need high public confidence that nobody will die or come back with cancer. People can accept risk, but I suspect even 10% will be too high. To seriously discuss those kinds of odds at all means a lot of preliminaries, like a protracted moon base and dropping supplies and robots down on Mars first. And that's not exactly science fiction anymore. We could be talking even just a decade. Every extra year improves all our associated technologies and lowers the mission cost. So we are not necessarily contemplating a few trays of plants growing a prefabricated habitation module as part of a $500 billion mission where the ship has a good odds of becoming a coffin. By the time the first mission is a go, we might be in a position to contemplate landing automated assemblers who can just get their reactor set up and start milling out heavy items like growing vats, glass, or even main components of HABs and solar panels. We would just assemble and install the small expensive electronic and mechanical bits on arrival. Not everything is necessarily heavy though. Aerogel is a potentially awesome insulator for space applications. It's ultra light, so it could be easily transported along, and it's also typically made of silicon, which is abundant on basically every rock in the solar system, so we might be able to make it on site anyway. It's also translucent and can now be made transparent, so I could easily imagine us opting for domes made of 2 layers of glass or polycarbonate with aerogel sandwiched between. Done right, that might make for a very shatter-resistant dome. Speaking of dome glass and breakage, on places like the moon where micrometeors commonly rain on the surface or in space, such panels would be even better with multiple layers and wire mesh woven in for added strength and fracture resistance. But on Mars, our concern is more about scratching and wear from the dust storms. Now, a note on that. We tend to portray those dust storms on Mars as being wildly powerful affairs, but the wind speed on those famous storms is typically 10 or 20 miles per hour, or 16 to 32 kilometers per hour, and can get up much faster. About every 3 Martian years, that's 5.5 Earth years, these storms become planet-wide and can move as fast as 60 miles or 100 kilometers per hour. Here's the thing though, the air is very thin, and you wouldn't be getting thrown around in that. Indeed, you would probably have problems flying a kite. Think of the force on a light breezy day, not a hurricane, even when the wind is moving at hurricane speed there. On a typical day, you wouldn't really notice it, but you would notice the accumulation. The storm would be depositing a lot of dust, and that dust is small electrostatic particles, which makes them stick to everything, as we found with our rovers, which get filthy fast. Now, this is manageable for manned missions because we can't just have someone go out and brush the solar panels off after storms, and a scratch-resistant coating should let them easily have lifetimes in excess of the mission duration. But for domes and panels that need to be operating, and preferably with minimal human effort, a robot window and panel cleaner, or even scratch polisher, seems a good plan. I would personally bet on that being tech that makes rapid strides in the next decade, given the success of robot vacuum cleaners, mops, and lawn mowers, to see robot solar panel and window cleaners. Of course, we usually clean with water, and that might be tricky on Mars. On the other hand, we need a water source for those domes, and a setup that allows the robots to spray water under a pressurized cup while it cleans them, then lets it dump that muddy water into the domes for the plants to use as soil might work very well. If filtered anyway. Now, I mentioned heavy metals earlier and perchlorates, and that's probably the next topic to address. Chlorine-based compounds actually are pretty valuable for a lot of applications on Mars, including making fuel and air, and indeed make for good antifreeze, which is handy on a cold planet, so we're interested in extracting them rather than just getting rid of them. They are water-soluble, which is partly why I often talk about algae vats in the context of terraforming alien soils. We can use algae for removing heavy metals from wastewater. That's been under study for decades now for use back here on Earth. I recently saw a study in Frontiers of Environmental Science last year, synthetic biology-based approaches for microalgal bioremoval of heavy metals from wastewater effluents, where they said they had studied 49 unique genes for their bioremoval properties of various heavy metals. So I think there's definitely room to be considering genetically engineered algae for soil and water reclamation in both our own future and Mars, and sooner than later. Centrifuging is an option too, of course. That can get pretty energy intensive at the large scale though, and while we can always get freebies on our heating bill by using electricity to power something and then let its waste heat warm us, Mars is pretty cold, so we need more than that to stay warm, especially in the context of insulated and airtight living, working, and growing spaces. It's not just humans that need to be warm, and plants also have their own different needs when it comes to safe temperature and humidity, as well as air composition, which having many airtight domes lets us fiddle with. Not to imply we just want to go nuts on nuclear or solar power there, though you might have to go nuts with excess heat for the purpose of terraforming or paraterraforming, which is where you dome large chunks of a planet over and terraform under the domes. An alternative thought, especially seeing the gravity on Mars is much lower than Earth and may require spin gravity to be added to the equation for us and animals to stay healthy, is spinning habitat areas. This typically involves a wide ring or cylinder with a tilted floor to combine centrifugal force with natural gravity, what we call a rotor-city or rotor-hab. See the Megastructural Compendium for details. Big tall cylinders have other advantages too, especially for insulation and shielding, and are easier to build on low gravity places with little to no wind pushing them over. A big thing to think about here is usable space or volume from stacking multiple levels with minimal surface area exposed to the outside, while still conforming to a structure commonly accepted on Earth for habitation, the skyscraper. This is probably an outer shell with normal gravity and some spinning interior sections, and maybe much underground too, but might be a preferable arrangement over our normal notion of sprawling domes, or used in tandem with them, like the foothills of a mountain. The outer shell of shielding is your expensive bit. The more surface area, the more air you leak, heat you leak, damage you take, and radiation you need to stop. So minimizing that is ideal, and a cylinder gets you way more interior area per surface than a typical rectangle. Spin gravity aside, a cylinder or ring or circular dome is also a good shape for plant growth, as you don't need as much insulation and don't get as much air and water leakage if you have less surface area. There's always going to be losses, and for that matter, recycling still has losses, and a place like Mars, or the spaceships that get there, need to work to be very good at recycling. In the short term though, it's not like energy is hyper abundant on Mars. As it is mostly an airless desert, we're not needing to be super concerned about maximum safety with early or nuclear power there, but also makes it a pretty good place for power beaming too, especially if you have an orbital network there from the get-go. Solar power always works great in space, even if it's 45% of the strength at Mars of what it is in Earth orbit, and power beaming works well there too, but so does concentrating light with mirrors in orbit. It wouldn't take too much sophistication to get a thin mirror sent in a capsule to Mars and have it spin itself out in a big wide lens focused down on a base on Mars. They can keep that power going even at nighttime. A satellite above you when it's dark isn't necessarily in the planet's shadow, and a ring of power satellites would always have light on most of them and could shift power to ground-side locations as needed. Early on, it would seem easier and cheaper to bring solar panels from home and drop them off in orbit, rather than trying to get them ground-side and installed. So let's consider a hypothetical case. It's the year 2060, and our outpost on Mars is one of the couple dozen run by various countries, multinational agreements, or private companies. There's maybe 500 people on Mars. Every big country wants a base there and can have it these days for an initial entry cost of tens of billions and about $1 billion in annual upkeep. Our base is a private one, but receives a lot of funding and logistical help from various countries, and we basically just grow food as one of our missions and study botany and ecology as our other, with a long-term goal of paraterraforming our location just south of Elysium Mons and Elysium Planitia. We have a 100 kilowatt nuclear reactor that's essentially black box technology with an anticipated lifespan of 30 years, and we are 10 years into that. We have some ground-side solar and limited chemical and organic fuels, plus batteries, but we rent beaming time from the network of satellites overhead who can send power not only to us, but also to vehicles that are parked. The positioning system isn't good enough at tracking to allow power beaming to mobile vehicles like back on Earth, but it can recharge them when they pause. This system is expanding and improving, and is expected to become the mainstay for small bases on Mars. We have a trio of big robotic land crawlers who do nothing but drive north and collect ice from a base there and come back with it in a never-ending circuit, bringing 50,000 liters of new water to us each week. We lose a couple thousand liters in that same time to exports of food and losses to a never-perfect containment system, but we're bringing in a net 2.5 million liters of water each year, 660,000 gallons. We have found that between our hydroponics, aquaponics, and water reserves making up most of our water on hand, we can still create a new square meter of soil under a dome for every 100 liters of water we get, or 1 hectare for every million liters, or 100,000 gallons per acre, or about 2.5 gallons per square foot. That's not exactly a one-time investment. We anticipate leaking water from our domes fast enough that we need to replenish it every 25 years, which is actually an amazing reclamation rate. Which means once we've built enough domes to cover about 60 hectares or 150 acres, we'll either be needing new land crawlers to run up to the North Pole if we want to keep expanding, assuming one hasn't broken down irreparably by then, or to have built a pipeline. Realistically, that's not in the cards anytime soon, thousands of kilometers of piping, but bulldozing a better makeshift road there might be. Either way, on a planet of 500 people where most of the food is still imported or made at local bases, that's a lot of growing space that we need to keep up with current food needs, which is mostly done hydroponically anyway. We don't have that many domes yet, and currently it takes up a big chunk of the domes we do have. We are the medicine and luxury goods place, so to speak, where things like coffee and orange juice and bananas and such can get grown, and where there are actual animals and non-food crops. We are less a farm than an ecological research station, garden park, and zoo, and a lot of the budget from home comes from groups and wealthy individuals who endow a new dome for a dedicated purpose by paying for the plant, animal, seed, or embryo to come in on the next Aldrin cycler. There's talk of building big solar mirrors, and there has been some prototypes. Mars is almost all prototype something or other, but we do have mirrors made of sheets of glass with layers of wire mesh and aerogel sandwiched in them, on domes made of aluminum with very thick earth sides. Some domes are long tunnels or rectangles, but the main work is a growing collection of geodesic domes 100 meters wide and arranged in a hexagonal pattern, with each empty space between being filled with storage and other facilities, including living quarters for our 10-person crew, and occasional visitors from other bases, as we're the closest thing to a resort on the Red Planet. Each of those domes, which currently number 12, is 0.785 hectares or 1.94 acres, and each is designed to be a semi-self-sufficient ecosystem, emphasis on semi, as it takes a lot of effort to keep these going. All in all, such an operation is set to expand as long as we can locally fabricate dome glass, can keep bringing in power and sunlight, and keep finding water and nitrogen. Supplemental lighting can be electric, or can be reflected down by mirrors in space, on the ground or on local towers reflecting light in. You can expand as quickly as your technology and resources let you add domes and make soil, and we are creating new soil on top of the old, typically scraping the existing regolith off and lining the bottom with a moisture-proof layer and processing the heck out of the future soil. We usually grow very simple grasses in domes in the first seasons, which can be grazed by animals, with the resulting manure added back into the soil mix. There is the other half of the farming. To leave our narrative tale behind, Mars isn't really able to support a heavy meat diet for inhabitants, but there is lots of room for fish and even chickens or larger livestock, like sheep or goats. It raises the question of when the first animal goes to Mars and what it would be. I would guess it would be one of fish, ants, or bees. As for four-legged critters, I would make a joke about it probably being a rat since they always find a way on ships, but they've only ever gotten to space as contained lab rats, and that's probably how they'll first get to Mars. I don't think it would be long before someone arranged to ship a dog or cat to Mars. Generally, we assume that cows will be among the last well-known critters to make the journey, as even a baby cow is nearly adult human weight and more inside a month or two, and even our most optimistic travel time to Mars without massive advances in propulsion take longer than that. Plus, beef isn't well known for its efficiency compared to other meat animals and isn't the only source of dairy. The usual assumption is that we would send lone female critters and lots of frozen sperm or even fertilized embryos for implantation, which circumvents the inbreeding issue, but realistically I think we'll have gotten our artificial wombs pretty good by the time we're importing arcs worth of critters to Mars, so weight might not matter much. There are also all sorts of problems with creatures with social needs that we discussed in more detail in our episode Exporting Earth, and we also dipped into ecological issues of alien worlds more there too. There is also the possibility of cellular agriculture to support a taste for meat, if we want it, but we don't want to ship up Bessie the cow. For that to work, we need to make some kind of nutrient solution in order to grow animal cells directly, and then 3D print those cells into dinner. Several companies have been successful doing this already, and although we're still figuring out how to make lab-grown meats more like a fillet and less like a blob, by the time we need Martian meals, there's good reason to think we'll have figured things out. The good news is farming on Mars should be much easier than on the Moon. The bad news though is that while a lot of our Mars plans and equipment can be more easily proof-tested on the Moon before being used on Mars, basically nothing involving farming and domes will really translate over. More good news is that while the sunlight is dimmer on Mars, it's enough for essentially any plant, though many of the most sun-loving would not thrive away from the equatorial region of Mars, and may need supplemental lighting even there. There are many different ways to concentrate light if it's needed, and it will depend on many different factors, a lot of which we can't foresee yet, which works best or easiest and becomes the norm. If we begin to see more cold climate greenhouses emerging here on Earth, that's likely to tell us much about how to best do it on Mars, and vice versa, those experiments there may help us learn how to better green our own Arctic regions and tundra if we wish to do so. The other good news is that while we don't know how humans will fare under Martian gravity or other animals, it seems likely that most plants will do well, and insects and aquatic life also, though until we get there and test it out, there is more speculation than information available. As always, we need to head out to space to learn how to live there. But the time is coming soon when we will, and one day soon you or maybe your great-grandchildren might be farming out in space, helping bring life to a new world. So we have a couple of announcements coming up as well as our upcoming schedule as we get ready to head into 2023. But first, a question folks who watch the show sometimes ask is if a STEM career in science, technology, engineering, or math is for them. And one of the factors that can never be ignored is if your future career is going to actually pay decent. And if you're curious, the Bureau of Labor and Statistics cites folks in STEM earning 238% more than is typical for non-STEM careers, or $95 for every 40 others make. So if you enjoy science-focused shows like our own and have been considering going into a STEM field, there's a ton of good reasons to follow that dream. A lot of folks also worry that it might be too hard, and science definitely needs some brains and willpower, and it helps to have a good learning partner like our friends at Brilliant. Brilliant focuses on interactive and hands-on learning and breaking big important concepts down to understandable and interactive pieces like they do in their Intro to Algebra lessons. The best way to learn math, science, and computer science is by interactive problem solving. With thousands of lessons and more being added each month, Brilliant can help you reach your goals. In just 15 minutes a day with bite-sized lessons, you can master topics that you once thought impossible, be it the basics like fractions or advanced topics like calculus. Learn the core concepts so you can help pioneer new innovations. With Brilliant, you can learn at your own pace, learn on the go, and learn a little something new every day. To get started for free, visit brilliant.org/IsaacArthur or click on the link in the description, and the first 200 people will get 20% off Brilliant's annual premium subscription. Before we get to the upcoming schedule, some of you probably noticed that today's episode is available in 4K resolution, and so was Sunday's Sci-Fi Sunday episode, Planetary Civil Wars. I've had folks requesting that we do that for some time, and I noticed that these days more than half our animations and footage is in 4K resolution anyway, and some of the animations just look so much nicer in their full resolution, so I figured we would try it on a few episodes. It takes a fair amount of extra rendering and uploading time, and that might turn out to be prohibitive in the long term, and there will be spots in the episodes where it's still 1080p or even lower, but I figured we should at least try it out, and I hope those watching on 4K devices are enjoying the higher resolution. Also, today happens to be my mother's 74th birthday, so I wanted to wish her a happy birthday, and as she does often watch this show, thanks for everything, Mom, and I love you, and I hope you've had another excellent year as this one draws to a close, because you've helped make so many of mine wonderful. Speaking of closing out the year, our normal time for our live stream Q&A would have fallen on Christmas Day, and with 3 new little kids in the house, that doesn't seem a great plan on my end. So we're shifting that to Saturday, December 31st, to head on the afternoon before New Year's. As we usually do Sundays, for those who can't join us then, this is a great chance to get your questions about the show and its topics answered. Before then though, we still have a couple more episodes, starting next week by asking whether or not our universe might be a black hole, as some believe, and also if it might be possible to live inside black holes. And we'll be closing out the year by exploring the future of transhumanism and humanity. If you want alerts when those and other episodes come out, don't forget to subscribe to the channel and hit the notifications bell. And if you enjoyed today's episode and would like to help support future episodes, please visit our website, isaacarthur.net, for ways to donate, or become a show patron over at Patreon. Those and other options, like our awesome social media forums for discussing futuristic concepts, can be found in the links in the description. Until next time, thanks for watching and have a great week.